No, I'm good.
So good morning, everyone. We are going to have Professor Mariya Toneva to give us the talk. Mariya Toneva is a tenure track faculty at the Max Planck Institute for Southwest Systems, where she leads the BRAIN team. And her research is at the intersection of machine learning, natural language processing, and neuroscience. Let's welcome Dr. Mariya.
Hi, everyone. Just a quick moment. Okay. Okay. I see it in the corner here and down.
Oh, there.
Yes. Huh. Oh, good. Okay. Perfect. Yes. Hi, everyone. Hi, thanks a lot for the introduction, and I'm really, really happy to be here. Thanks for having me. Today I'll be telling you about our research on language modeling beyond language modeling, and it sounds pretty meta, but I will explain what I mean in a second. But first I wanted to tell you a little bit about our new group, which is called Bridging AI in Neuroscience. And so we started it about a year ago at the Max Planck Institute for Software Systems in Saarbrücken, Germany. And we are focused on establishing a direct connection between the brain and AI systems with really two main goals. So the first goal is to have direct transfer of brain insight to AI systems, specifically natural language processing systems. And the second goal is to have computational models of cognitive functions in the brain. So to help us understand more about the mechanisms that allow the brain to have these amazing cognitive abilities that we have. So some research highlights from, just very briefly, from these two directions is the first one gave us the first evidence that we can use brain recordings of people processing very complex language, like a chapter of a book, to improve a model's, actually a state-of-the-art model's understanding and generalization of language to language beyond its training distribution. And in the second direction, we have had some new mechanistic insights into how different kinds of context affects the way we process language. So for example, if I ask you a question, how does that affect your processing of following language? So this whole research direction has really been helped by these recent advances in natural language processing that have been due to language models. So I know you're all familiar with language models and ChatGPT, and even so I moved to Germany very recently, about a year ago, and I don't speak very much German, but I try to improve, and I listen to the radio on my way to work. And so I still don't understand too much, but about February a year ago, I heard ChatGPT on the radio. So even the Saarbrücken radio is talking about ChatGPT. And of course, this recent progress has been driven by language models, which, as you know, have been trained to predict missing words in a sentence. And they've had such amazing performance across different language tasks. But what I'll be telling you today is actually not only are they good at different language tasks, but they're also really good at aligning with the way that we process language in our brains. So they are really good at predicting what our brain activity would have been if we had seen a particular kind of text. So how do we actually evaluate this kind of alignment? So we and others have proposed a pipeline that's pretty standard at this point. So what we have is a natural text, like a chapter of a book, that we present to a person as we scan their brain activity. So they read this chapter word by word, and we scan their brain activity as they read. And we can present the same text to a natural language processing system. So for example, a language model like GPT or BERT. And we can extract the representations from activations, latent activations in this model at different layers. And we can look at what is the activity that's induced by this text that we present to the person, in particular areas in the brain where we know from previous work language is processed. And then we can ask, what is this alignment between these two representations of language? So we have one representation from a language model and one representation from the brain. That's both are elicited by the same underlying text. So how do we evaluate this alignment? Well, we can use very simple machine learning techniques. So we can learn a function f that takes as input the representations from the model, so the activations that are elicited by a text, and predict as output the activations in the human brain when those activations are elicited by the same text. And importantly here, we not only learn this function, but we also, of course, need to test how well we can predict some held out brain recordings that we've never used during training and we have not seen before. So this is how we generalize. We test how well this function f that we learned actually generalizes to unseen data. So just one more slide in terms of the specifics of how we learn this function f. So here we, in order to learn this function, we need to parameterize it in some way. So we very often parameterize it as a linear function. So essentially we learn the linear combinations, the linear combination of these input features from the language model that best predict a particular XYZ coordinate in the brain. And there's some evidence that a nonlinear function f can also lead to better alignment, but all the results I'll show you today make this linear assumption, and that's a very often made assumption in the field. And the reason is that it's efficient to show us a significant alignment between the two, so we pick the simplest possible function, f. And so once we have parameterized this function, we learn it from the data directly. So we do this in using very simple techniques. So we train this function, the parameters of the function f, using cross-validation, and we regularize the learning using ridge penalty usually. And we evaluate in 3 simple steps. So the first one, of course, is to make predictions for data that we have not used during training. So we're actually predicting brain data that we haven't seen before. And the second one is once we have made a prediction for each XYZ coordinate in the brain, we want to see how well did we actually predict this data. So we want to compare it to the true brain data. And we often do this using simple Pearson correlation. So for all the test samples, we have a prediction and we have the true test data, brain data. And we can calculate the Pearson correlation across these test samples. So at the end, we may have a number like 0.4 Pearson correlation for a particular XYZ coordinate. What does that mean? Is that a good number? So we also need this third final step of evaluation, which is stringent hypothesis testing, to make sure that this underlying relationship that we are evaluating actually is different from chance. So this is often a permutation test followed by multiple comparison corrections. So after this 3 steps of evaluation, the numbers that survive all of these steps we know are not due to chance. So indeed, they show a significant relationship between the representation in the language model and the representation in the brain, as both are processing the same text. So all the numbers I'll show you today have survived this stringent evaluation approach. Great, so using this kind of pipeline, we can evaluate this alignment that already exists between language models and language in the brain. And here I'll show you an example from some recent work. And it's not important to understand everything, but here what I'm showing you is the ability to predict the brain using a representation from a language model. And the number that I'm plotting is normalized by essentially the signal-to-noise ratio in the brain signal. So it's the amount of variance that's explainable that we can actually predict using the brain, the model. So I can talk more about that if you're interested. Now, but essentially, if we're able to predict all of the variance that is possible to predict, then we would expect a number close to 1. And we can see that actually many voxels, so by the way, this is a brain. So this is the left and the right hemisphere, and it's cut computationally along some edges, and so it's flattened. And so for example, let's see if the cursor shows here. I don't think so, but for example, one important language region is the auditory cortex, which is here on the bottom left. Great. Oh, great. Thank you. Yeah. Perfect, thanks. Yeah, so this is the auditory cortex, and we see the left and the right hemisphere light up pretty similarly and are well predicted. And so what I want to show you with this is that there's many regions that are predicted really well, almost up to the maximum amount of variance that we can hope to explain, because again, we cannot explain 100% of the variance in the signal because there's noise in it. So we can predict up to an estimated noise ceiling. But there's also a lot of regions that we cannot predict up to noise ceiling. So for example, even this region here, some of it we can predict well, but actually about half of it we cannot predict very well at all. So it's even close to zero zero predictivity here. So the point here is that the actual brain alignment of these models is really impressive, but it's not perfect yet. So what can we do to improve it? So this leads to two main questions. The first one is actually what are the reasons to begin with for this impressive brain alignment that we already see? So this is a question because, again, these models learn language in a very different way from how we learn language. So they learn language with a simple objective function to predict the next word. So what are the reasons that they already align with the brain to such a good degree? And the second one is we see that they're not perfect, so how can we actually improve this alignment even further? And I'll tell you about our work in both of these directions. But first, to begin with this, what are the reasons for this alignment? Well, it's actually challenging to reason about this because one way you can think of it is we are trying to compare one black box language model to another black box, the human brain. So it's a bit difficult to reason about these two black boxes. So the way we go about it in our group is to use to investigate this via a perturbation approach, in which we have this standard pipeline where we evaluate the alignment between the original language model and the brain, but we also have a second step in which we make an interpretable perturbation to the model, in which we either add or remove some interpretable information from the model, and then we evaluate how does that added or removed information affect the alignment with the brain after this perturbation. So here, if we see that there is significant difference between the brain alignment before and after this perturbation, then we can say something about this added or removed information in terms of how important it is for the language processing in particular regions in the brain. So this is an approach that is very common in our group, and we have found it helpful in trying to reason about these relationships between the models and the brain. So I'll give you one example of this work, which was recently done by a research intern in our group, Suba Reddy, and we presented this at NeurIPS just about a month ago. So here, what Suba was interested in was this finding that if you look across different layers in a model, in a language model, you see that the best brain alignment occurs around the midpoint of the model. So not at the end of the model, not at the beginning of the model, but about the midpoint in terms of layer depth. And this has been observed several times in the literature, and people have speculated that the reason for this is because these language models are trained in a self-supervised way. So both the input and the output of the model relate to word-level information. So perhaps the middle layers are where the most high-level information is occurring that aligns with the kind of processing we have in these high-level language regions. Well, that's good, but it actually doesn't agree with our understanding from the natural language processing literature, in which people have used probing approaches to understand what kind of linguistic information is contained in the different layers of the models. So people have shown that the middle layers are actually best for syntactic processing rather than this high-level semantic information. So Suba was interested in understanding actually what linguistic properties underlie this brain alignment that we observe across different layers in the models, and specifically these middle layers. So we're going to use this perturbation approach here to answer this question. And just to show you the perturbation approach that's specific to this work, the pipeline is the following. So we have this original stimulus, which in this case is an auditory audio story. We have a language model, we have fMRI recordings for the story, and we can calculate this original brain alignment in the very same way that we have already seen. And now we have this added linguistic property. And now I'll tell you about what kinds of linguistic properties we're looking at. But you can imagine here, for example, the depth of a syntactic tree. So for each sentence in the original stimulus, there is a depth of a syntactic tree. And now we can computationally remove the information that's related to the syntactic tree, to the depth of the syntactic tree, from the representations from the model. And we can test how does this removal actually affect the brain alignment that we observe from the original model. So if we see a significant decrease in brain alignment after we remove information about the syntactic tree, then we can say that this information about the tree depth is important for specific processing in the brain. So here we are going to investigate the effects of different syntactic and semantic and surface properties that people have studied in the literature. So specifically we're focusing on the sentence length, the depth of a syntactic tree, the top constituents in the syntactic parse, the tense, the subject, and the object number. So these are all properties that have been previously investigated by work, and what previous work has shown is that the surface properties are contained in early layers of the model. The syntactic properties are more present in the middle layers of the model, and the semantic properties are present from middle to late layers. So for this, we use a fMRI recordings data set from an open source data, which is called the narratives. And this has 18 subjects that are listening to a naturalistic story. And we annotate the linguistic properties on our own, and we use, so here I'm saying we're using BERT, but we also have GPT results, GPT-2 results that are very similar to what I'm going to show you now and are in the paper. So first off, we wanted to test how does this removal of these different properties actually work. So is it successful? So what we can do is we can here I'm showing these different properties, and we have the before and after column. So before is the probing accuracy for this property before removal, and after is the probing accuracy for the same property after removal. So we would expect, of course, that if we're able to remove the property successfully, then the ability to probe, to decode this property from the representations after we remove it will be a chance, which is what we see. So we see that so the bolded numbers are before, and then the corresponding ones are on the right side. So we see a significant decrease in ability to predict these properties from the layers after we remove this property, which is something that we expect, and this was a sanity check. So we see that indeed we can successfully remove the linear contribution of these properties from the representations in the model. So how does that affect the alignment now with the brain, which is the main research question? So here, what I'm going to show you now is the average alignment across the entire brain. So we saw this big flat map of the brain before. So here we're averaging across all of those different XYZ coordinates in the brain. And so what we see here in blue is the actual pre-trained original alignment. So this is without removing any properties. So we see that this pre-trained alignment is about 0.1. Pearson correlation, again, these are all numbers that have survived this stringent hypothesis testing. So they're all significantly different from chance. And now we have a random vector that we can randomly create for different words, and we see that it's much lower. So actually, there's a substantial difference between the way that a pre-trained model can predict the brain activity and this random vector can predict the brain activity. So now what happens when we remove different properties that we're interested in? So for example, a surface property like word length. So we see a substantial decrease in this alignment here. And this is also different from just removing any random vector, because one question you might have is, what if this removal is just messing up with the representations, and we can now not align these representations well to the brain? We see that, in fact, removing the specific property is much more impactful than just removing a random vector from the representation. So we see that actually removing the word length, the surface property, affects this alignment with the brain significantly. Great, so we have these other properties, though, that we are even more interested in, like syntactic and semantic properties. So we see that across the board, they all impact this alignment significantly, but we actually don't see much difference across these different features. And one reason is that here we're actually looking across all the different layers. So this is an average across the whole brain and across all the different layers in the model. So of course, we're going to break this down a little bit to see whether there's any differences between these different properties. But first, about this question about what is the alignment across the different layers in the brain. So as we saw, as we talked a little bit, we see that this pre-trained BERT alignment here in blue, we see that it's high in the middle of the model and it's lower in the beginning and the end of the model. So we're trying to explain this. Why is this happening? So we see that after removal of a syntactic property like top constituents, we see that this kind of trend that's high in the middle is actually gone now. And of course, we're going to quantify this, but I just wanted to show it to you qualitatively here. So how can we actually quantify this? Well, we can look at what is the decrease in brain alignment, what is the relationship of this decrease across layers with the decrease in our ability to probe for this property from the different layers after we remove the property. So here we're going to look at this correlation across the different language regions. So these are regions, all regions where previous work has told us that language should be processed. So one thing I want to show you here, for some of you who are familiar with language in the brain, so we're talking about both the left and the right hemisphere. So maybe from your neuroscience classes or psychology classes, you might have heard that language is left lateralized, so only the left side of the brain participates in language processing. That is actually not what we see when we move to very complex stimuli like a narrative. So when somebody is engaging in trying to understand a story, both the left and the right hemisphere are very much engaged and are processing language. And so this kind of goes a little bit into the direction of what is language. And so, for example, Sian talked about how language and reasoning actually happen in different regions in the brain. It really depends on how you define language. So if your definition is very limited and, for example, you're just talking about single words processing or sentence processing, you might see very constrained set of regions that participate in this. But as you move towards more naturalistic processing of language, there's a lot of other functions that become involved, and then you see a broader set of regions that become activated. So how does this correlation look like in these canonical language regions? Well, we see that our ability to remove the top constituents, so a syntactic property, has a lot of impact in these canonical regions, especially on the left side, actually. So they're very localized here on the left side and more distributed on the right side of the brain, which is actually something that's was quite new when we saw this, because usually when we talk about naturalistic story understanding, we see very similar results both on the left and the right side of the brain. And we see that these other properties, even though on across layers, when you average across layers, we see very similar effect. We see that actually the shape across the layers is actually less correlated with the way that the ability to decode this property varies across the layers in these canonical language regions. So the syntactic properties are the ones that really impact this shape of alignment across the layers. So here, to go back to this research questions, so what are the reasons for the impressive alignment of the language regions? We investigate this with a perturbation approach, and one partial reason that we see is this joint processing of syntactic properties, both by the brain and the language model. So I'm saying it's only a partial reason because, let me just go back real quick, because even though we see that there is a significant decrease in alignment from the original model, we have actually not reached this random performance yet. So there's a lot more properties that are important for this alignment between the brain and the model that we have actually not accounted for here. And then now on to the second part, which is actually how do we improve this alignment that we see that it's not perfect yet. So one question is, why do we even want to improve this alignment? Well, the way that I think of it is that by improving this alignment with the brain, we actually create even better what I call model organisms of the brain. So for language processing, we don't have very good model organisms that are capable of complex language processing like what humans are capable of. For vision, we have model organisms like different kinds of monkeys and even cats and some mice. But for language, we don't have this kind of model organism. And so it's important to have a computational model that we can do these different perturbations in and different interventions, which are not ethical to do in human beings. So by actually improving their alignment with the brain, we can better use them as such model organisms. And then the second part that we also have some evidence for is that by actually improving the model's alignment with the brain, we can also improve the way that it generalizes to unseen situations. So here I will talk to you about two results in this direction in which we improve this alignment with specifically linguistic processing in the brain. And the first one, we move beyond language modeling in the sense that we move beyond models that do next word prediction by training the models to further summarize narratives. And we see that actually improves the alignment with the brain in these language regions. And the second one is by actually incorporating information from the visual modality. And we see that that actually improves alignment with linguistic processing in the brain. So I'll tell you mostly about the first direction, and the second one I have a few results, but it's more preliminary. So I'll share just a few results from it. Great, so the first one here, this is based on work that wants to have true language understanding in models. And one way that people have proposed to have models that have true understanding is to further train models to summarize narratives rather than just predict the next word. So these models are given as input, let's say a chapter of a book, and are trained to predict as output a summary of this chapter, which can be much shorter than the actual input. So let's say the chapter is 3,000 words and the summary is 300 words. So during training, the model is able to actually produce the summary of the chapter. And so one question there is, are these models really truly developing deeper understanding of language, which relates to this question that was talked about in the introduction to today, which is how do we evaluate understanding in models in general? And so here we're going to use the one system that we have to truly understand language, which is the human brain, to actually evaluate the model's understanding of narratives. So first off, what makes narrative summarization different from language modeling? Well, the first part that we actually touched upon already is that such a model that is able to summarize a chapter in much shorter amount of text should be able to capture the critical information by integrating over these long contexts. And the second one is to actually generate a summary that is good. This language model should understand, or a good summary would actually have an understanding of the overall story arc and the relationships between these key narrative elements, such as characters and the different emotions that characters have. So then to recap, this language modeling may be learning some kind of shallow heuristics, whereas the narrative summarization has been proposed to move beyond this and have deeper understanding of language. So we're going to investigate this using this brain alignment technique that we talked about already. So essentially we have these two types of models. On the left side we have a language model, and on the right side we have a model that has been further fine-tuned for narrative summarization. We're going to extract activations from these models, and we'll look at how well do they align with brain recordings of people understanding a narrative. Great. So then the hypothesis here is that if the model that's trained to summarize narratives has greater alignment with the human brain than the language model, then it's capturing more brain-relevant information. And here, importantly, we're going to look at 4 different models, and we're going to look at their counterparts that are trained further on this book summarization dataset called BookSum. So the important thing here is that we're always comparing models within model family. So we're not going to look at 2 different models that are trained with different architecture, that are trained on totally different data. So we're always comparing a pre-trained model, base model, with its counterpart that's further trained on a book summarization dataset. And this really ensures this good comparison, and we can say what this brain alignment difference is due to because we know what the differences are between these models. So the first question is, are these book sum models, the ones that are trained for book summarization, are they actually developing a deeper understanding of language? So we can look at here is the actual brain alignment of these two different models. So on the x-axis, we have the brain alignment in Pearson correlation, and on the x-axis, in the y-axis, we have the different models pairs. So in blue, we have the base pre-trained models, so the language models, and the orange ones are the ones that are trained on the book sum data set further. So we see that across these pairs of models, the book sum models always predict the brain better than these original language models. So we see that training language models to summarize narratives does in fact improve the brain alignment. And here you may notice that these numbers, the Pearson correlations, are very small. And again, they have passed all kinds of significance tests. But also I wanted to mention here that this is the most restrictive setting that we have here. So we're averaging across the entire brain and across all the different layers and context lengths of these models. And there's some layers that align better than others and some context lengths that align better than others. So here, this is an average across all of these. So we're really not cherry picking the best result, but we're really looking across the entire brain and across the entire models. Great, so here we have this result, but really why do models that are trained to summarize narratives predict brain activity better? So we went a little bit further to understand this. And so first we did a lot of experiments to rule out possible confounding factors for this improved brain alignment. So for example, we saw that it's not entirely due to this extra training on the book summarization data set, because we can look at the language models and we can fine-tune them with the language modeling objective on the same data set. So the two models have now seen exactly the same data, but with a different task. And we can see that that does not actually improve the brain alignment of these language models. So the actual training objective does matter. We see that it's not just due to the language modeling ability. So we see that the book sum models, unsurprisingly, are not as good of language models as the language models are. So they're not as good at predicting the next word. And even though they're not as good at predicting the next word, they still align with the brain better. And then we also see that it's not entirely due to the summarization objective, because if we train a model to summarize non-narrative articles, so if we train it to summarize articles from newspapers, then the model is not as good at predicting the brain as it is when we're training it to summarize narratives. So these are all experiments that helped us rule out possible confounding variables. But what does actually affect this improved brain alignment? So in order to answer this, we did a little bit more interpretability methods to help us understand. So here we labeled all the words in the Harry Potter data set. So, oh, I forgot to mention, this brain data is from people reading a chapter of Harry Potter. And so there's many important elements in this chapter. So for example, this chapter is when Harry Potter learns how to fly on the broom for the first time. So there's a lot of important motion elements. And so we can label each word in the Harry Potter chapter with either a character, a motion, or emotion label. Specific characters, motion, and emotion label. And we can see how does the alignment from the summarization model actually affect, how is it affected for the specific parts of the narrative that include characters, emotions, and motions. So we see that for specifically for the characters, whenever we see characters in the chapter, we see the greatest decrease in alignment between the language model and the book sum data set, which means that the parts in the narrative where we see characters are actually the most enhanced by this ability of the model to summarize the narrative. So here we essentially can say that the book sum models have greater brain alignment than these base models across all of these three different important narrative features like characters, emotions, and motions. So in general here, we believe that this improved brain alignment is really suggesting deeper understanding of these models. And so we're seeing this because of three main results. So the first one is that actually the summarization models have improved brain alignment for important narrative elements like characters, emotions, and motions. The second one that actually I didn't talk about in this talk, but is in the paper, is that we only see this improvement in brain alignment when we look at contexts that are beyond 20 words, which is where we would expect summarization to actually kick in. So if we're just looking at 2 or 3 words, we don't expect that a model that's learned to summarize can help us predict the brain better for those words. And the third one is that there's many possible confounders for this. So when we did our best to rule out these different confounders, like the language modeling ability, domain similarity, and the training objective. So we are confident that now models that are trained to summarize narratives are developing deeper language understanding because of their improved brain alignment that we see. And now on to the very last part, which is just a few slides on actually incorporating information from the visual modality to help us have better linguistic processing in the model. So here in this work, we are looking at recent advances in multimodal transformers that jointly learn the representation of language from vision, text, and audio. So here we want to ask, what is the effect of this visual information on the actual linguistic processing in the model? And we're going to investigate this by looking at what is the alignment of this model with multimodal brain recordings. So we have these collaborators who are collecting fMRI recordings to people watching Friends, the TV show, all 10 seasons of Friends. So it's, yeah, it's about 100 hours of data. So it's 6 people watching Friends, and we're looking at how is a multimodal video transformer aligning with these multimodal brain recordings. And here we use specifically this multimodal transformer called Neural Reserve, which jointly learns from text, audio, and vision, and this won the Best Paper Award at CVPR a few years back. And we chose this model very pragmatically because it's one of the only open source models that actually works really well on videos. And here, essentially, very quickly about this model. So it has 3 different encoders for the visual frames, the text, and the audio. And it learns a joint representation of them during training. And is pre-trained on 20 million videos in an unsupervised way that are taken from YouTube. So the prediction objective here is a held out, a masked token in either the language, either the text or the audio. So it's essentially mass language modeling objective, but it's using both video, text, and audio to make this prediction. So the way we're going to investigate this is we have the video, the vision aspect, and the audio aspect, and we're going to ask, does a joint representation that's jointly learned over vision and language, does it predict the language regions in the brain better than just if we look at the language representations? So we can look across these, again, canonical language regions, and we can compare these 2 representations and how well they align with the brain. And we see that the joint representation of vision and audio does in fact predict some of these language regions better than just the language representation, meaning that the vision actually enhances the ability to process language in these specific regions. And just one last result on this, of course, in our group, we're really interested in the why question. So why does vision contribute to language? Well, one idea is that maybe it's contributing via this mass language modeling objective. So, for example, if this part of the brain is predicting the next word, if the vision is helping the model predict the next word, then it's possible why this vision can help predict this brain region better. So we can investigate this via this perturbation approach where we remove information that's related to the next token that the model is trying to predict. And we see that in fact does reduce the alignment quite a bit with these regions where vision is important. So it does appear that the visual input is enhancing the actual prediction of the upcoming words in the model, and that is leading to this ability to predict the brain regions better. But there's more work to be done to really understand the full set of contributions of vision to language, because as we see, this alignment is still not at 0. So there's still some substantial brain alignment that we observe even after removing this information about upcoming characters. So just to wrap up here, the second direction was how do we actually improve this alignment with the brain further, because we see that language models align with the brain but are not perfectly aligned with the brain. So we can do this in moving beyond language modeling. So looking at objectives that help us predict higher order information and also incorporating other modalities other than language. And overall, this whole research direction of using language models as motor organisms for language comprehension in the brain is really enabled by this very recent successes in language models. And when compared to just 5-6 years ago now, today's models are much better at having this complex linguistic meaning and continue to increase their alignment with the brain. And so we're only at the beginning of uncovering this overlap between information processing and machines and brains. And there's many more exciting directions as we move ahead in using natural language processing systems as model organisms for human language processing. And so just to give you a sneak preview into what I'm thinking about for some future directions in this area is, so we are currently thinking about how to evaluate and improve the long-term memory of these language models. Because as we've seen, actual long-range understanding is a big part of how we process natural language in humans. So first, we are focused on looking at what are some new tasks to test this long-term retention. And here we're working with some collaborators at Princeton, at UT Austin, and at Intel. And together we are developing these new tasks and actually collecting a big data set of humans who have recently read a book, and we test their long-term retention of different parts of the book. And we're only in the beginning of collecting this data set, but I already find myself partial to this piece of Twitter wisdom, which is if you think machine learning is hard, you should try data collection, which really it is. But really, jokes aside, when we complete this data collection process, I really think that it's going to be a large human baseline for this long-term retention of language models, which we don't even know what it should be. So we have no human baseline for this kind of long-term retention on the order of books. So we're really excited about this effort, and we believe that when we complete this, we'll have this big baseline that we can actually understand how models are doing at retaining this information over long periods of time. So thank you so much for your attention, and I look forward to the discussions and questions.
Any questions, please?
Thank you.
Sure, yeah.
Thanks for the cool talk. So I was wondering if learning about alignment with the brain can tell us about the choices we make in NLP, like the pre-training objectives, tokenization, or whatever else. Like if you compare across GPT-2 and Word, did you see anything that's interesting?
Mm-hmm. Yeah, that's exactly one direction in the group, is to use the brain alignment as an evaluation metric, essentially, because there was this question of how do we evaluate understanding and what makes a good model. So we can look at behavioral output on different kinds of tasks, but of course that's really related to the data set we're testing on. We can look at next word prediction, but that's not really the downstream performance that we care about very often. And so this brain alignment is one metric that we're really trying to use. And we have used it in different ways. So one specific way that we've used the brain alignment in the past that has been successful was to look at long context processing and trying to understand how much of the long context are models retaining. And we see that, for example, a model like Transformer XL, which combines both a recurrent architecture with a transformer architecture, is able to retain a lot more long context than models like BERT and even GPT-2 as well. So we can look at, essentially, when we provide more and more context, how much does the alignment improve with the brain, and if the model is able to maintain a lot of context, then we expect it to continue improving up to the point where it cannot make use of the context anymore. And we only see this in some models and not others.
Thank you for the great talk. It was really interesting. I want to ask something about data because, as I said, it's complicated and messy to collect all this data. And so I was specifically wondering about your opinion on the trade-off that you can make to get the best signal-to-noise ratio, because I guess you can either collect a lot of data, a lot of naturalistic data in a few number of subjects and try to go for as much context and as much variety, a large amount of data per subject, or you can go into the direction of more controlled stimuli that are maybe, let's say, have a smaller context range, but then in a higher number of subjects that might increase the signal-to-noise ratio. And I feel like people are kind of drifting into these two different directions. And I was wondering, what's your opinion on finding the best compromise, or what direction would you go into?
Mm-hmm. Yes, exactly right. So there are these two camps of collecting a lot of data for a few subjects, or a little data but for many subjects. And this is because we have constraints of time and money, right? So of course, ideally we would have a lot of data for a lot of subjects. Yes. So my hope is that we get to the lot of data and a lot of subjects. So right now we're actually collecting a whole book. So it's 10 hours of data for, we're trying to do 40 subjects. This will be the biggest data set that exists. So in both fMRI and MEG. And so my hope is that we get there and we have the funds to do it. So we just need to find the subjects. But in our work, it's very helpful to have a lot of data per subject, because otherwise you're not able to actually train these models, this function F that relates the representation from the model to the brain. And we see that having more data there does help. There are some diminishing returns also on it. But you cannot do that with just 100 samples per person. So you do need some amount, significant amount of data per person to actually be able to do this. But my hope is that with more funds becoming available, we actually create also bigger data sets. And another really promising direction is to have models that are not person-dependent, so where you can use data from multiple subjects together, and you can gain from this than just training independent models. But actually, that's not been successful so far. There's many people working on this, but essentially, there's no model that I know of that is better by combining data from multiple subjects because of variability across subjects. But I think that's not a fundamental limitation. It's just a limitation of the methods we have now, and that will be improved in the future.
So how do you deal with time? So the transformer is running everything in parallel, but people are hearing these this text in time.
Mm-hmm. Yeah, so yeah, great question. I didn't talk about that. So essentially, we have a sliding window throughout the story, and we provide of text, and we provide the sliding window to the model to obtain the activations that we use to relate to the model. So we just slide the window by a token each time, and we get the representation of each token that's contextualized by the context in this context window. So that's how we deal with time.
And then you do correlations for each individual time step.
Yeah, so we have the training, this function F that we train, we have some training data, which is about 80% of our data that's contiguous. So let's say the first 80% of the data is for training, and then across this training samples, each sample is a data point. So each time point we use is a training sample of this function F.
Thanks for the talk. Very fascinating work. I have two questions. One is about word surprisal, because BERT is basically computing probabilities over closed procedures, hidden word modeling. And it has been shown already to be linked to N400, event-related potentials, and so on. And I was thinking if that is something also that you want to work on, because for me, it sounds fascinating, linking this back to work on memory, what the language model has as memory, and then how it is surprised by seeing words that it's processing on the fly. That's my first question. And my second was more relating to what you just said about variability in people, because there are some research in, for instance, learning, where you really see differences between learners, whether they're visualizers or verbalizers, or when they're going to have a multimodal task. Some learners will be better at some tasks because if you give it a multimodal output, they're more visualizing people or have a visualizing aptitude, and whether that is something that you can account for in the data.
Mm-hmm. Yeah, really, really interesting questions. So the first one is about trying to model these different processes that we know do exist in the brain, like, for example, the N400, which is occurs when somebody is surprised at seeing some word in some context semantically. And so we see that models are quite good at modeling this as well. So they relate to this surprisal, both at the behavioral level, but also at the neural level. And having context, actually, the reason why models are so good at this and are better than other models, like let's say word2vec, is that we have this contextualization that we can have with the language models of representations for particular words. And if we look at, we also have work on MEG in which you can see the time course throughout the word, and you can see that this time around 400 milliseconds, which is where you observe the M400 effect, is quite well predicted by the model. But also other parts are also well predicted, like around 100 to 150 milliseconds, which is more processing the word form. And that's actually even better predicted. So a lot of the information that we have in the language model is related to this. And maybe we can talk offline also about other kinds of information that we see that's common between them. And the second question is super interesting. Yeah, it's an open research question. So we think that these kinds of models, the multimodal models, can tell us more about also integration of information in the brain as well. So we do know some things. There's some modularity that exists in terms of modalities in the brain, like vision and language. But there's also a point where the two meet and we form understanding of the event that is going on. And so we hope that some of these models and new ones that are coming up as well can help us understand about this integration between vision and language.
Yeah, thanks for the talk, really interesting. My question is about the first part where you do the perturbations. And so you said that, and you showed that for the different tasks that you remove, you get very similar results actually in terms of brain alignment. I was wondering, to what extent, when you are removing one task, to what extent are you sort of removing just the ability of the model to do that task, and to what extent are you maybe removing more general like syntactic information? So maybe empirically speaking, if say you train the model to no longer be able to predict the top constituent, do you also remove its ability to do the other tasks like tree depth, or are those unaffected?
Mm-hmm. Yeah, really important question. We did experiments to test this. So we looked at how does a model that has removed linear relationship to the syntactic tree depth, how does that affect the stop constituents, and the opposite way. There is a little bit of difference in terms of just looking at a base model versus one that has, let's say, top constituents removed, but it's not substantial. So there's not substantial decrease, yeah. And it's related to also the correlations that exist between these, the signals in the data originally, right? So if, let's say, the syntactic tree depth is very correlated with the top constituents, of course, when you're removing information about top constituents, you're going to affect information about tree depth. So it's just about having a very diverse corpus that's large, where you can see these not great correlations between these different kinds of information. We can see in our corpus, there's a little bit of correlation, but it's not substantial. Yeah, a really important question.
Okay, so Mariya is giving a super interesting talk, and a lot of people is apparently interested to that. But due to the time limit, we will have one last question. So,
can you maybe take
organizer
question? Sorry, we can talk more.
Oh yeah, sure.
Yeah, this was a very nice talk. Thank you very much. So I liked very much also this Sumbook project, or Sumbook experiments. Also where you showed where information about the characters motions, emotion are important. So do you think then we should train our language models having an emphasis on these? And my second question is, do you intend also to study such effects with visual data? Because I can imagine that characters, motion, actions are quite important in visual data.
Yeah. Yeah, oh, great questions. Yeah, so we did this work before ChatGPT. So we know now that these models are trained with different kinds of tasks, not just an next word prediction, right? So I think that the field is moving towards a more diverse set of tasks with instruction tuning and so on. So I think the field has recognized this, that next word prediction is not the only one that matters. Of course, it's a nice task to get us self-supervised training on a lot of data, but it's not actually the thing that gets us to amazing performance on many diverse tasks. So yeah, I firmly believe that summarization at least is related to what is happening in the brain when we are processing very complex stimuli. And your question about videos is really, really great. I would love to study this, and we're thinking a little bit about it in terms of the multimodal Friends recordings. So we're looking also at captions, having models that caption different scenes and looking at how does that relate to the processing in different language regions. But it's a bit challenging because we don't have the human gold standard annotation of what's happening in the scene. So, but we're trying to use automated techniques to do that. Thank you. Thanks a lot. Yeah, thank you all for the great questions. And I'll be around the whole day and also now. Mm-hmm.
Okay.
Oh, okay, good.
So you have question, right?
Yeah. So if you, for the goal of having like a mechanistic understanding or so of the brain, I think that's also part of the goal. Can it be that you have a very high alignment, but the brain got there in a totally different way than your model? For example, now you were using like linear models to align them then, but if you use some very advanced non-linear model, I can imagine you can really maximize alignment with fMRI, but like, does that teach you all the more then?
Mm-hmm. Yeah, really important philosophical question. It's a question that the field as a whole is struggling with, and it's something that I care a lot about. So this is all about alignment at the representation level. So we just have two representations, and we have no idea how we got there, right? So the mechanism for one representation can be super different from the mechanism that led us to the second representation. And we're just checking, is the information that's contained in these representations is similar or different? So the mechanism is the next step. So trying to understand how, when we alter the mechanism in the model, how does that actually affect the representation and its alignment with the brain? Because we cannot really alter the mechanism in the brain. We can. There's things like TMS and other kinds of devices that lets us, but they're invasive, right? So you actually change temporarily the way that the brain is responding. So I think that's part of understanding the full mechanism in the brain. But now in the more short term, I'm excited about this perturbation approach, but more on the mechanism in the model actually. So this was, all that I showed was on the representation level, but you can also think of these mechanistic interpretability techniques that are coming up now in natural language processing, in which you have the computational graph of the model and you alter that in different ways in trying to understand how does that affect the representation that you get and its alignment with the brain. So that's how I'm thinking about moving beyond the representation level and going to the mechanism. But really important next step.
Okay, thank you very much for the very interesting talk. So we're going to have a coffee break to 10:30. So enjoy the coffee.
Thank you.
Thank you very much.
Yeah, thank you.
Oh, here. Wow. Oh, that's so slick.
Yeah, it's almost true.
Yeah, but I mean, well set into the table.